All right, let's get started. We're very happy to have Itai Gurvich come all the way from Kerala, talking about
all the way.
dynamic.
Okay, thanks for the opportunity to present here. So, broadly, my interest is usually on optimization of queuing systems, and this is related, but in some sense, it's also a significant departure from what I've been usually doing and kind of outside of my comfort zone. But I thought that actually presenting it in a double ECS context is a good opportunity to get feedback, because this is kind of a model in search for an application. So if you have any ideas or feedback, I'll be glad to get them. So I'm going to talk about dynamic control of matching queues. And this is joint work with Amy Ward, who's a colleague of mine in USC and also a queuing theorist. And I'm not going to do much queuing theory. In a sense, I'm going to talk more about the problem than about the solution that we propose. So I'll try to be very clear about what the actual challenge is. So here's the example that I'm going to use throughout. I'm going to generalize it to general structures, but it's good to think about this example. So think about 4 queues. So we have dynamic arrivals according to some process, so random dynamic arrivals. And jobs or customers, however you want to call them, arrive in wait in one of these queues. So I have 4 types of queues arriving dynamically. And I have 2 types of matchings here, A and B. And what happens is when I activate matching A, I simultaneously deplete 1 job from each of these queues. So this is not like a natural service system where I choose which job to deplete when I can take an action, but actually I simultaneously, every time I take a job from here and here, I basically match them and they leave the system together. This is why this is a matching queue. Similarly here, if I activate matching B, it means I'm going to take 1 job from each of these queues, which means that all of these queues have to be must have jobs in them for me to be able to activate B.
And,
yes.
And you take the job at the very last bottom of the queue?
Whenever I take a job, I take the job at the head of the line. Mm-hmm. So notice that, I think you've seen a talk here recently about kidney exchanges, etc. What I'm matching here is queues. So I'm not matching individual people standing in the queue. I'm not matching the second person in this queue with the first here. I'm actually just matching this queue with this queue and taking the first from each of the queues. So service is instantaneous, so there's no capacity. Once I can perform the matching, I will instantaneously perform it, or once I choose to do it, depending on my optimality criterion, I will match the jobs and they will live the system. And my question is going to be, when should I perform these matchings? So given the state of each of these queues, I have a number of jobs here, 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 and here. When should I perform one of the matchings? And I'll be clear about the objective function. Any question about the setting though? So the components are dynamic arrivals into queues and instantaneous matchings that deplete multiple jobs at once.
Well, sorry.
Yes?
You just said instantaneous matchings that treat multiple jobs at once?
Yes, so if I activate matching A and there's a job here and a job here, I match the 2 and they leave.
I see.
That's the matching action. So if there's no one here, I cannot use this matching.
You can't activate A.
You cannot activate A if there's no one here. You cannot activate B if one of these queues is empty.
Do you have a example that we can keep in mind? Is this
Yes,
I'll
try to give one. Yes.
Okay, and so matching B actually makes it triple.
Yes.
Okay, so it's unlike the matching that I would call matching.
So there's a trade-off. Here's a trade-off. So let's think about the trade-off. So if I have 1 job in each of the queues 1, 2, and 3, I can either perform a matching of type A, in which case this job and this job are matched and leave the system. So I've reduced my total queues by 2. Or I can say, well, maybe I should wait, because there are dynamic arrivals until a job of type 4 arrives, at which time I'll be able to get rid of 3 jobs at once. So this is where this 3 versus 2 comes into play. So this is the challenge when you think about how do I control the system in terms of capturing this fact that sometimes I better wait to get some queue with customers in it. Yes?
Do the queues have capacities?
Finite capacities, no. There can be an infinite number of people waiting.
Okay.
So this optimization is a problem only when the queue lengths are very small. Otherwise, you just go with the maximum matching.
If all queues are full,
Yeah.
then it's easier to think about how to solve
Only
this.
in the case when the thing is like.
It's only the case where some queues visit 0 with some reasonable frequency. Yes, that's when this is reasonable. If you have an infinite supply of jobs here, then and you're just trying to maximize number of matchings, then just match whenever you can.
Just a small comment. So,
Sure.
So to get this kind of significant pupil weight or not, maybe it's not even, you need to not even be match 3 jobs together. You can generalize to some kind of network and now which kind of link you want to choose to match. That kind of problem also have similar tests like that.
So again, what's the problem?
So you were trying to motivate here that either wait for the B to match so you can match 3
Right.
together.
Mm-hmm.
So in a little bit more general, maybe a network matching, just matching 2, but then you constrain the what kind of pairs you can match together.
Right.
It's going to have the same effect.
Right. So yes. So you can have very different network charges, in which case the trade-off is not necessarily 3 versus 2, but a bit different, right? What is interesting in this network, which is different than the networks that we in operations are used to think about, is that there's no capacity here. Jobs are both supply and demand. So when a job of type 1 is demand looking for a job to be matched with to leave the system, but a job of type 1 is also capacity for jobs of type 2, right? Because for a job of type 2 to leave the system, it has to be matched either with a 1 or with a 3 and 4. So jobs have a dual role here, being both demand on their own, but also supply for some other jobs. So that kind of makes this setting a bit different than what I'm used to think about. Any questions?
Is there an objective? Like what?
Yes, I will show it in the next slide. So here's the general setting and the objective function. So I'm going to have multiple such queues, multiple types of matchings, and I'm going to have a graph that maps the queues to matchings. In the previous slide, this graph was this very simple graph when I have 2 matchings, but it can be general, and you can define it by a matrix that says that a matrix M, such that Mij equals 1 if job type I is in matching J, participates in matching J. You can have an arbitrary number of matchings, and what I'm trying to decide is how many times to activate each matching on a finite horizon 0U. And what we're trying to do is minimize total cost over a finite horizon 0 to U, subject to natural constraints, which are just the dynamic constraints, that the queue is the queue at time 0, plus how many arrived, so that you should read this as vectors, plus how many arrived minus how many I matched. So if I employ matching J for a certain number of times through the matrix M, it will map into how many times did I deplete the queue of type I. So this is just the dynamics constraint.
What are all these variables?
Okay, good question. So Q is just the queue length. So Q of T is the queue length at time T.
So I'm trying to minimize I could think of C as being linear, for example.
Think of C as being linear, in which case you're minimizing the linear holding cost over a finite horizon, and yes. By choosing a control D, which basically is going to tell me up to a given time, up to any time T, how many times do I activate matching J. So for example, here I'm going to have dA and d sub B, and d sub A of T will tell me how many times did I activate matching A up to time T.
Can you activate 2 disjoint matchings simultaneously?
Yes.
So isn't this like set covered?
At any given time it might be, but the problem is that I have dynamically. Right. The problem is, in a sense, if you want to think about, if I could, and I will return to this point, ideally, so let's say I make my first decision at a given time T, and that's the end of my horizon. What I would want to do is ignore all the mistakes I did up to that point, put everybody back in the queues, and then do the optimal matching, right? The problem is when I do dynamic these decisions, how do I achieve kind of that bound? Then I'll return to this point.
Can I ask a question?
Sure.
So is this, if you're not looking for applications yet, is it that you have just different ways of packing objects into a shipping container or something like that? Would that be an application?
If
So
they
if you-
arrive, yes.
If you go back to the previous slide, you can put the first 2 objects into a shipping container and that's it. Or
Yes.
you can put the last 3 into container B.
Right.
And you're trying to get rid of your inventory instead of keeping it around. Would that
So kind of dynamic packing. Kind of, yeah.
dynamic packing.
Yeah.
But then, in this case, if the last queue doesn't have anything, I cannot pack into B.
Yeah, you're constraining yourself that you have to fill it before you can ship it out, maybe, so, which may not be realistic. So, but good point.
Yeah. For those who are probabilistically inclined, just to mention that this is kind of seems to be undefined because I have random processes here and I have taken no expectations here. So this objective function is really a random variable, but I'm going to show a very strong sense of optimality that's going to be basic stochastic ordering, in which case it's actually okay to talk about this as a random variable. So here's the application from which we kind of started, but I don't want to claim, and I'm not claiming that we're solving this problem. That's why I'm still saying this is in search for an application. So kidney exchanges is something that have been studied recently by actually economists in various places. And you can think about each of these queues as corresponding to a type of pairs. So pairs of people arrive to the kidney exchange. One person needs a kidney, the other person can donate a kidney, but he cannot donate the kidney to his friend. But what you might be able to do is take this pair of people and match it with another pair of people where the needy person matches with the donor of one pair and vice versa. In which case you do a swap of kidneys. Doesn't sound very well, but you do a swap of kidneys and they all leave the system happy with new functioning kidneys. And there the decision is very similar to this, but there are many complications in kidney exchanges that we are not covering, so this is kind of maybe a first step to help study this setting. But again, the fundamental question is, how do I make my control decisions? Do I act myopically or should I do something a bit smarter? And of course, the trade-off is sometimes similar to here in the sense that in kidneys, there is also very long chains. So you might sometimes be able to, it might be worthwhile to keep one pair available for a long chain that will arrive of people of 10 pairs such that they swap kidneys along the chain and everybody gets kidneys. Yes, talking about kidneys is a bit weird, but that's the application. Okay, so here's the problem. So the problem is we're trying to minimize this cost of holding cost over a finite horizon, subject to the dynamics constraint that what I have in each queue is what I had at time 0 plus what arrived minus what was matched. Matchings has to be an increasing process. I cannot match negative. I cannot put people back in the queue. I can only match and have people leave the system. And this constraint only says that you cannot activate a matching when there's one of the queues that is connected to this matching is empty. That's all it says. So to return to this example, I cannot activate matching B here because there are no jobs of type 4 here, and I need all 3 to be able to perform the matching.
Sorry.
Yes?
I'm sorry, I don't know if I missed it. Do we know anything about the arrivals? Are they like Poisson distribution?
Yeah, so I'm going to assume that the arrivals are non-homogeneous Poisson, but this is
And so lambda
1, lambda 2,
rates.
they're the rates
Okay.
of the Poisson process. In a sense, the stochastic properties of the arrival process are not playing a key role in the result. For modeling purposes, it's okay to think about that. Okay, so this problem is clearly difficult. I haven't tried to solve it, say, using dynamic program, but I think it would be very hard. What I'm going to propose is a solution that is nearly optimal in some sense. And more importantly, I think captures the essence of the trade-off here. So any questions before I get to thinking about the solution? So it might be good to start with just thinking deterministically. So forget about all the randomness that is in this system. Ignore the discrete nature of jobs, and then assume that the number of jobs arriving by time t is just the integral of the instantaneous arrival rate. So you have some arrivals. And if you just stop at time t, and this is your only point in which you make a decision, what you want to do is minimize the cost of the queues, subject to the constraint that the queue after you perform your matching is what you had initially plus however arrived minus how much you match. So it's the same problem, but everything deterministic. Okay. And this has two purposes. First, it allows me to classify into different networks, but it also shows you something that I think it's related to something that was asked here, that ideally what I would want to do is exactly do this. So if the system was deterministic, at each given time t, I would want to ignore the whole history and perform a matching to minimize the instantaneous cost. So if at each time t I could return backwards, reshuffle my arrivals, and then do the optimal matching at time t, that's what I would do. It also gives you a sense of how good, at least if I, before I introduce variability, how well can I do in terms of matching everyone or not? So the first question you might want to ask yourself, well, maybe here, can I actually match everyone? Maybe I can achieve 0 queues, or can I not? In which case, I'll be in a different setting. So we say that the network is balanced if for each time t, I can actually find a matching, activation of the matchings that puts the queues at 0, that matches whoever arrived by that time. Unbalanced if there are some moments in time where I cannot match everyone, so I'll have to have significant queues, and something in between which is alternating. This is actually not that important for the remainder of the talk. I will return to this with the numerical examples. Yes, so let me just continue here. So here's how we think about this problem of matching. What you want to do, and I think this is what is interesting about the solution, is simplify the problem by identifying a metric that tells me how far am I from being able to match everyone. Right? And being able or not being able to match everyone depends on how many arrivals I had up to a given time. Right? Because it depends on the state of the queues. So let's go in that direction. Suppose you take no actions until time t, and at time t, I just want to match everyone. So I had q sub 0 people at time 0. I have a vector of arrivals a of t, so a1 of t is how many arrives to q1, a2 of t to q2. And I'm looking for a vector d that says that allows me to match all of these customers by saying you should activate matching A 10 times, activate matching B 20 times. This does not have to have a feasible solution. I might have a state in the queues where I actually cannot match everyone. However, if you take this system of this linear system and you write its dual, you arrive to this problem. This is kind of easy to derive. And duality theory, basic duality theory, just tells you that a feasible solution, a non-negative feasible solution here exists, if and only if there exists an optimal solution y to the dual that satisfies this, that y transpose q0 plus a of t equals 0. Okay.
I'm sorry.
Yes.
So D is the vector that says that how many times you should activate each matching.
Yes.
Okay.
D is the vector that says how many you should activate.
Does it say at which time though?
No. So here I'm taking the.
You just know how many times you should activate. You don't know when.
Even not that. I'm just saying, assume you don't do anything up to time t. For now. And then how many would you match at that time? So this is still not my solution. I'm just trying to construct my way to the solution. Here I'm saying, to start with, let's pretend that you do nothing up to time t. And
So
then you just try to match as many as you can.
Arrived.
Some jobs arrived, and time t you have some state of the queues, and you just
so
try.
that is set cover basically.
And it is that set cover.
Okay,
Yes.
okay.
So if there exists an optimal solution to the dual, this optimal solution seems to give you a sense of a metric. How far are you from being able to match everyone, in the sense that whenever you're able to match everyone, y transpose times your state is going to give you 0. Anything that is away from that will tell you that I'm not able to match everyone, and might give you, in a sense, a metric of how far you are from matching everyone. So that's why we call this the shortest process. So we take y to be a matrix that basically spans the solution to this dual. which spans the left null space of the matrix M, if you want to call it this way, but it spans the set of vectors y such that y transpose M equals 0. And we call it the shortage process based on that motivation that whenever this process is 0, it means that I have enough jobs in all of the queues that allows me to match everyone and empty all the queues simultaneously, which will not happen at all times. Okay. And the result, the first result is then that if you have a vector x such that x is orthogonal to this matrix y, then there is indeed a solution D such that MD equals x. This is what I just said to motivate this. If this equals 0, then you can indeed match everyone. For those who like algebra, this seems kind of obvious because what I'm doing here is I'm saying that if x basically is in the space of the columns of M. But there is something a bit more subtle here because I need D to be non-negative. So I'm not just requiring that x is a linear combination of the columns of M, I also require that the solution D is non-negative, and this is where the assumptions comes in. And I will translate this algebraic assumption to something very concrete on the network structure, what I'm assuming from the network. But the assumption is that the matrix M that specifies which job types are connected to which matching has to be such that if M times X is strictly positive, X is strictly positive. And this is not an innocent assumption. I will show you that it limits the networks that we can cover. Okay, so here's an example that might illustrate this idea of shortage a bit better. So back to this very basic network. The matrix M is 1, 1, 0, 0, and 0, 1, 1, 1. So 1, 1 because there is a row for each job type, so 4 rows. There is a column for each matching A and B. With matching A, I have job types 1 and 2. With matching B, I have job types 2, 3, and 4. One possible choice for the matrix Y that is orthogonal to this matrix M is this choice. It's one of the multiple choice. It's not unique. However, then if you look at the shortage process, just to verify it does the right thing, if I had no jobs at time 0, and at the time t I have 3 jobs in each of these queues, 5 jobs in the first queue, and 8 jobs in the second queue, then A3 minus A4 is 3 minus 3 is 0. A1 minus A2 plus half of the sum of these also gives you 0. You can verify that. And indeed here, and I said I motivate this by saying that the shortage equals to 0 when I can match everyone. And here indeed I can match everyone. So I'll activate matching B 3 times, in which case I'm going to take 3 from here, 3 from here, 3 from here. And I activate matching A 5 times, in which case I empty these 2 queues. So we've reduced. So you can think of it as a multidimensional kind of metric that says how far I am from being able to match everyone. Shortage is kind of an abuse of English here because this is going to have both negative and positive entries, so imbalance might be a more proper term. Any questions?
What is A again?
What?
A subgroup.
So A1 is the number of arrivals to Q1 by time t. So thanks for the question. A2 is the number of arrivals to Q2 by time t, A3 to Q3, and A4 to Q4.
Regardless of what the strategy you do.
Yeah, arrivals are exogenous. And here I'm just taking a scenario to illustrate this point. Of course, the challenge, yes.
Again?
Y is just a matrix that I define to be a matrix that spans this subspace. So it spans the vectors that are orthogonal to the matching matrix M. Any other questions? Of course, yes.
So the problem of if I give you like a vector of numbers and I'm asking you is and also those restrictions, and I ask you, is there a way such that I empty all the queues? That's empty hard, right? So it's empty hard. Okay.
This one.
Well, this is a special case of it.
Okay.
This seems an easy case of it. But
Yeah.
the general case, it's
So what is the general case? So what?
like I give you like just a set of restrictions, and like I give you a number of on each queue, and I ask you, is there a way such that I empty the queues?
Mm-hmm. So it's empty hard in the number of.
Queued and matching types.
Okay.
Right. Okay. Okay.
Yeah, in a sense, yeah, I know very little about complexity, and
Mm.
I haven't given thought here.
But you think,
and
for
if-
example, when these types are small, right?
Right, so if you have many types, then maybe it becomes more and more complicated. In a sense, also the result I'm going to show you reduces the dynamic problem to a static problem, but I'm not saying that the static problem is easy to solve.
Yeah.
But just that solving the dynamic is going to be as complicated as solving the static one. Yes, of course, the problem is if this imbalance is 0, then I have no question. I just match everyone, and queues are going to be 0. The challenge is going to be, how do I spread the queues? How do I balance the queues when actually this is not 0? When I'm not able to match everyone, which matching should I use? Okay. The problem here, of course, is that I have the fact that these are matching queues imposes a limitation on what I can do, because here, for example, I cannot really empty. If I wanted, if these queues were not constrained one by the other, I could direct all the capacity of A to this queue and empty it. If there were independent queues that I'm just looking when to serve which queue. But because there are only 2 jobs here and this is capacity for this, the most I can do is decrease this queue by 2. Which shows that you need kind of enough information in the system to optimize it. So it's not surprising that why this process is going to be multidimensional. Well, this is a point that is more relevant for people that have been doing queuing. And in queuing theory, when you have a system like this, you can usually reduce it to a one-dimensional question. Because I have so much freedom in the system, I can move queues from one place to the next. But here I cannot really do this. I'm very constrained by the fact that these are matching queues. So here's what is important. What this very simple algebra allows us to do, and this condition that I left on purpose vague, is to take this matching problem. Notice that this is the decision variable here is not only a process in T, it has a dimension of I times j. So the dimension of this is as the dimension of the number of classes multiplied by the number of matchings. So it's very significant, and what I'm going to show is that this is equivalent to a different problem where my decision variable is only I-dimensional, as the dimension of the number of queues. So for example, here instead of being 4 times 2, it's going to be just 4. Or instead of 6 here, actually, it's going to be 4. So here is a very different formulation that uses my notion of a shortage. It says that your decision variable q has to be such that y transpose q equals the shortage. And this is an exogenous input now. Remember the way I constructed this, this is independent of the way I'm actually taking actions. It just takes into account the arrival inputs and uses them as an input to the optimization problem. And I have some constraints on the queues. This just says that the queue cannot grow by more than the number of arrivals. So I cannot have queue of type 1 between S and T go up by more than the number of jobs that arrived out between S and T, which is kind of obvious, and that the queues are non-negative. And under our conditions, the 2 problems are equivalent. So that's the first important result here, that if you have this matrix condition that, again, I left so far fairly vague, it's enough for me to solve this much simpler problem. The dimension, the type of constraints is easier, and the dimension is lower. So admissibility here is not that important. So if I have a solution for this, I can generate a solution for this, and vice versa. Solve this problem and you get a solution for the other problem. There's a way to construct a solution for the regional problem.
So it's just duality.
It's basically, it's almost, yes. So the main lemma in proving this is just a duality result. It's fairly simple. There's no big steps here. What is still problematic here is that I have this constraint. So notice that if I remove this constraint, the problem becomes really trivial. Because if I remove this constraint, there's no dynamics anymore in the system. If I remove that constraint, I get this problem where my constraints are for each given t. So what you will do is forget about the integral. At each time t, choose your optimal q such that these two constraints hold, and it must be optimal because I'm pointwise doing the best possible thing in this problem. And so the solution of this, as I pointed out, is at each given point in time, minimize this, which just means minimize C of Q such that Y transpose Q equals S. And this is the optimal solution to this trivial problem. And this goes back to what I said before, that I call this a reshuffle lower bound. Because this pretends that at each time t, I can ignore all decisions I made up to that time, optimize as if nothing happened, and then move to the next decision time. So a way to reframe this question is, to rephrase what I'm going to do next is, say, how close can I get to this? This is clearly a lower bound, because I'm ignoring history. While taking into account the actual dynamics, how close can I get to this crude lower bound? Questions?
Where did you get the shortage process again? The S of t
Yes.
is
It's actually important for me. The S of t is defined like this. So
there's a y there as well.
Y is here.
So there's a constraint that y transpose qt is S of t, where the S of t also has y in it? The same y, or is it different?
Yes, it's the same Y. Yeah, it's the same Y. But this doesn't mean that Q is going to be equal to A, right? It just means because it's not a non-singular matrix. But there is Y on both sides. Indeed, yeah. But Y is not a decision variable. I fix it in advance in one of the multiple ways that satisfies this its property that this property, and that's it. And from there on, I just use it. And whatever choice I make, it's going to generate the same optimality results. Yes. So let me show you what the policy is. Let me ignore the previous slide. So the policy is very simple, and this is what I said is the reduction from dynamic to static kind of. I'm going to do review epochs. So let's say every 2 minutes, I'm going to look at the queues and solve a certain problem. Okay. So I have some choice of the review epochs, which one has to actually be careful about to get the optimality results. And at every subsequent review epoch, I'm going to solve this static kind of matching problem. It says minimize the queues subject to this shortage process constraint and the dynamics constraint. It says that when I make my decision now, the new queue has to be equal to the queue before my decision, plus however arrived between the two decisions, minus the amount that I'm going to match. So I'm just solving this at each given decision epoch. So it's just an algorithm for discrete review kind of solution. And my input to this problem is this shortage value, which again is just a mapping and aggregation through a matrix of the arrival processes. And you can equivalent if you're not happy with using history information, because this means I have to keep track of all the arrivals up to the time of decision, because this is an aggregation of the arrivals. You can define this equivalently using just the queues. So you look at the queues and you solve a static optimization problem at each review epoch. And of course, the the important thing, or the surprising, but what needs to be proved, is that this very naive thing, it just takes this, discretizes it, and solves it at discrete time points, actually achieves the crude lower bound that ignores any constraints, any dynamic constraints. Okay, so instead of a theorem, let me show you the results, some numbers. So quadratic costs, so we have 4 Qs. The Q, when the Q type I is equal to Qi, the cost is Ci Qi square, and I sum these up. So it's quadratic cost with these coefficients specifically for this numerical example. And what I'm going to do is I'm going to compare the cost under the lower bound, which is a crude lower bound, but it is a lower bound, with the results of my algorithm. And let me explain what you see here. So first of all, there is the cost. For the total cost, the lower bound cost is 4,063. The algorithm cost is 4,194, so there's 100 and something difference here, which is fairly small. And I'm not claiming that, I'm going to show you the exact statement, I'm not claiming that my algorithm is optimal. I'm claiming it's nearly optimal. So I will be able to relate this gap in numbers to a mathematical statement. What you see here is 4 sample paths of Qs. So for each of these Qs, I plot 2 things. The evolution of the Q, if I could follow the lower bound. So if at each point in time I could ignore history and put the Qs exactly at the optimal point. And the other sample path is the Q that I see when I use my algorithm. Okay, so I have an evolution of the 4 Qs with time. One under the lower bound, which is not really achievable, or not necessarily achievable, and one under my algorithm. And what seems to be here 4 lines is actually 8 lines. For each Q, 1, 2, 3, and 4, there is a line for the lower bound and for the algorithm, and they're practically indistinguishable. So the algorithm really follows the trajectory of the lower bound, or the unconstrained lower bound.
Is there any place where they're different that we can see?
They are different. I mean, if you take a section and inflate it, they're going to be slightly different. But the differences are going to be sufficiently small that the costs are not going to accumulate. And one reason you must see differences is that I'm making decisions only at discrete time points. Between the discrete time points, I'm actually letting the Qs go up. The lower bound is kind of continuously adjusting the Qs. So there's no way I'm going to track it perfectly. And this is why actually you have to be very careful in how you choose your discrete viewpoints, because you don't want to allow the cost gap to accumulate. You have to kind of control for things. Maybe here the picture is a bit clearer. So here there are a few of the Qs that remain at 0 all the time. Here I just changed the rival parameters. So here the rival parameters were 300, 600, 300, and 300. So this corresponds to a setting where you can see that I should be able to match everyone in a first order sense, because the rival here is 300, here and here is 300, but here is 600, which exactly you can split 300 to here and 300 to there. But of course, once you add the stochasticity, you still are going to have Qs. Here, you cannot even in first order match everyone, and the picture becomes a bit clearer. But again, you see that, so here the 2 lines corresponds to lower bound and algorithm, and you can see that they're very, very close.
Sorry, is this graph for that last example you said, where the rates were exactly?
No, this is the graph for the rates where they're exactly.
I see.
So if
we should, I mean, this should seem kind of like a random walk on a line when you can't go negative or something.
True. Yes, exactly. Because right. So your intuition is correct in the sense that if the rivals were really just a deterministic flow, I would have the Qs at 0 all the time. So the rest is just a symmetric random walk. It's just the noise around this mean.
So it should be like square root.
Yes. 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 The overall Qs are going to be like square root of the rivals. Yes. Yeah. Valid point. Here you're going to get more. Here you're going to get like order of the rivals Qs, but and then some fluctuations which are square root. Yes.
What's the lower bound algorithm?
The lower bound just does this. So I ignore all the dynamic constraints. At each time t,
I understand.
I just optimize this.
Okay.
I kind of ignore future or history, and I just look at the shortage process and optimize myopically at each given time t. Not just myopically, but also ignoring the past.
I mean, you should be able to ignore a history anyway, right? If we assume that they're Poissons.
Then if you like already matched them, you can't go back and like undo a match and bring them back into the
Wait,
queue and match.
history of matchings or history of arrivals? Because like the new.
No, the history of matchings.
Okay.
So I ignore any mistakes I've done in the past,
Okay.
and I'm allowing myself to say, if this is the number of arrivals I have by time t, how would I match them optimally? And then each time t, infinitesimal time t, I resolve this. And this is just, again, same example, time-varying arrivals. So arrivals are a constant plus a sinusoidal perturbation of that. And again, you see the same phenomena. So it's, yeah.
With the plot where things are exactly balanced,
Yes.
the viewpoint of like a random walk on a line that can't go negative, I mean, wouldn't you expect it to switch which cues were the ones that were constrained like infinitely often, like as you proceeded? And this is
When you expect to,
like usually a random walk
Mhm.
goes 50-50 plus or minus,
Yeah.
right? Will cross the origin infinitely many times as
Yes.
you proceed. And it seems like your plot is just like the two cues that are getting backed up are just staying backed up. Like,
well, first of all,
nice.
because this is my optimal thing to do, right? I have a cost function. I have a certain cost function that drives some queues to be bigger than others. Because my algorithm takes the cost into account. But
This is the example where they're balanced. We should expect them to be balanced.
the arrivals are balanced, but not necessarily the costs. So the way I distribute the effect of randomness across the different queues is not necessarily balanced. I might choose to hit by the randomness the cheaper queue more than I do the expensive queue. Okay. Let me say something about the condition, the main condition, which is, as I said, is not an innocent condition. So I said my main condition for this algorithm to work is something we call the match pooling condition, which is that if the matrix M, n vector x satisfy that mx is strictly greater than 0, then x must be strictly greater than 0. What does this mean for a network? It means that to match a positive number of jobs from each of the queues, I must use all the matchings. There's no redundancy in this network. If there is redundancy, I'll have a problem. I'll show you an example with redundancy. So look here. If the arrival rates are 1, 1, 1, 1, everything is balanced. At least in a deterministic way of thinking, I should be able to use matching A to match these two, because the arrival rate here and here are equal, and use matching B to match these two, because the arrival rates are equal. And at least at this first order sense, I don't have to use matching C. So I could almost remove C from the system. It's not entirely true because I might use C for the second order, the square root of n variability, but in first order I could ignore C. So this very simple example is actually not covered by our results, which you might find disturbing, and it relates to some phenomena that is known in queuing theory. But if I add an extra customer type or job type here to be served by C, then suddenly it does hold. Because now I cannot serve this new type here without using matching C in a significant way. So really the condition is you cannot have matchings that you can underutilize. If you have matchings that you can underutilize, then our results don't hold, and the reason is that because the analysis becomes much more sensitive. Everything that is going on with this matching is second order. It's the square root things. And you have to be very careful in how you manage that. So really it's a lack of redundancy requirement, as I said. We have a way to verify this match pooling condition, just an algebraic lemma that says you have to solve a set of linear programs, and under certain conditions or under certain outcomes will guarantee that the match pooling condition holds. And again, it boils down again to duality theory, fairly basic. Anyway, just to say that there is a way to verify this without actually plotting the network and or verifying it for each vector x. Okay, let me say just what the notion of optimality is that we have, because as I said, this is not truly optimal. It's just nearly optimal in some sense. So what we usually do in this type of queuing theory is to say we cannot really solve the optimization problem for the given system. Let me inflate the system. So instead of fixing a given system with a certain arrival rate lambda, or vector of arrival rate lambda, I'm going to inflate that. So I'm going to assume that I'm looking at a system with very, very high volume of input. I'm going to adjust my review time points. So my review time points are going to become, well, they're going to shrink, but they're going to remain kind of in a ratio to the scale of arrivals. And the arrival process is going to be inflated as well. So think about a system where instead of having an arrival rate of 1 to each queue, you have an arrival rate of 1,000. The bigger it is, the more precise is my recommendation. And yes, so basically the point is I inflate the arrival rates at proportional to a scalar n. And the bottom line is this. I will read through this, but the bottom line is that my algorithm generates an outcome or a cost that is at most little o of square root of n from the optimum. So the error, there is error. There is an optimality gap, but it grows slower than a central limit theorem rate. So slower than square root of n. This is again kind of the standard notion of optimality in this field of research. This is small o. So it grows smaller than square root of n. That's the statement, and it says, the theorem says that if you fix your time horizon under appropriate assumption, which is this condition on the matrix M, and with the cost function C being Lipschitz, then not only is my lower bound really a lower bound, but I'm actually approaching it at this rate. So actually the costs are going to inflate themselves at rate n, but I'm going to remain close to them by at most little o of square root of n. That's what's going on.
So to get this, it's important that you choose a rate by whatever the formulation in the field. Is Tm equal to that? Or it's
very important how I choose this. So the way I choose my discrete review points, the points at which I'm actually performing a matching, is actually very important. And if you choose this in a different way, then you're going to.
Can you give a little bit more insight on why we have this formulation?
Yes, so I'll get to that. I'll get to a bit of insight on that. Just a few words on, so we don't need the cost function actually to be Lipschitz. If it's not Lipschitz, we have a different statement for the optimality result. And there is a large family of functions that satisfy our properties. One thing that is important is if you think, and it's related to this, partially answers your question, the trajectory of the lower bound that I'm trying to follow this one. So the trajectory of the lower bound is determined by solving kind of pointwise this simple local optimization problem. But it's important for me that as I change the right-hand side S, this optimal solution changes in a continuous way so that then I can actually track it. If it suddenly jumps, so suddenly it says that now your queues are 10 and 1,000, and the next second it has to be 1,010, then there is a problem. I cannot really track this. So you need some continuity properties on this. So we impose some conditions on the function family that guarantee that you have this type of continuity, that when you in subsequent time epochs solve the optimization problem, your solution doesn't change much. And I asked much smarter optimization people than myself for input on this, and then I wrote in the paper that I asked much smarter optimization people so that the referees don't complain. Yes, and so the conditions are fairly standard. On the cost function, we have some conditions. Let me now get to the point that you mentioned, which is how is this choice, why is the discrete review, or what should we be careful about? What allows you to track the queues? Okay. Let me go back to actually to the network. See if we can think about the algorithm. So what helps me in not making decisions continually is that if you wait enough, you'll have some arrivals in each of these queues. And having positive queues already helps, because then I have the freedom to use multiple matchings. Right? If I have queues both here and both here, all of these queues have some jobs in them, then suddenly I have the freedom of actually choosing between A and B. Well, if one of the queues were empty here, I don't have this freedom. Okay? That doesn't resolve still. This is why I'm solving it in discrete time points and not continuously. I want to make sure I have enough queues in front of me when I make my decisions. Then there's some other things that allow you to, or our main condition on the matrix, allows you to make sure that at each review time point, my queue actually equals to this lower bound trajectory. So I have the lower bound trajectory I want to follow, and I actually manage to track it. So this is the key lemma in the result. It says that at each review time point, you're actually able to perform the exact number of matchings you need to put yourself in the trajectory of the lower bound. And once this is true, then this explains the graph you saw before. It explains the fact that I see very similar trajectories under my algorithm and under the lower bound. Yes, well, this is here. And remember, I said that the algorithm has this dynamics constraint, which is disturbing because if I could remove this constraint here, I will be again in this formulation, which is the lower bound formulation, where I have no dynamics constraint. What this lemma shows is basically, the essence of the lemma is that I can remove this constraint. So I've imposed enough conditions on the network that allows me to remove the constraint. That's basically the essence. And that's why I said the way you could interpret a result is the saying, what are the conditions on the network in which the result that you get is as if at each given time point you can ignore history and match as many as you want. This is just a restatement of the asymptotic lower bound, so skip it. There is, just to conclude, this is closely related to some queuing literature, which I haven't discussed and I'm not going to discuss. It's related to some recent work on kidney exchanges. So for example, what is interesting, so there is this person in Boston College called Utku Unver, and he was looking at this matching in kidney exchanges using a dynamic programming approach, but he imposed the assumption that at all times all the queues are big. And that basically moves you away from the boundary and allows you to do many things. So it simplifies, in a sense it trivializes the problem, but his setting is actually much more general than the one that we have. So there's other complexities in what he did. So to summarize, so there is, I think, as far as I know, so in EE there are actually many papers which have, I think, the word matching in them. But usually it's matching input to output, right? Like in switches, but I'm not familiar enough to say for sure. So this is a bit different. What is special about this model is this dual role of input as both demand and supply, which I think is interesting. And we provide kind of conditions under which we can generate an asymptotically optimal solution. And as I said, this is the first time it's the first problem like this that I've been working on, and I also have no clue what would be a continuation of this, and I'm still looking for where it's relevant and what can be done with it. Partially, this is related to some things that are done in network routing in what's called fork join queues, but still the connection is kind of vague. That's all I have to contribute on this one. Questions? Yes?
So you mentioned some related work, which so you've got a sort of discrete approximation where you let the queues get big and then you clear them all as best you can and then you repeat, right?
Yes.
And you mentioned, and you're saying that this does nearly as well as if you didn't have the timing constraint.
If you didn't have the dependence between your current decision and decisions you made in the past.
Right.
Yes.
And so the other approach that you mentioned just like 2 minutes ago was this: if you keep the queues to be big.
Yes.
Right. And so you could imagine knowing how much variance there is in the arrival process,
Right.
right? You keep them at some minimum level so that the constraint on queues not going below 0 is never binding,
Yes.
right? Is it possible to compare I mean, this should also give you some approximation, right? Unless you have to keep the queues too big all the time to keep this, to make it so the constraint of going below 0 is never binding, right? So
Yeah, so the question is, what do you lose? What does it mean to keep them sufficiently positive, and what do you lose in terms of cost? What Unver did is assume exogenously that the arrivals are so big that there's no way you're going to empty the queue. There's no actions you can take that will put the queues at the boundary. The queues are just huge to start with, and it just considers not the minimization of holding costs, but actually maximizing the output, how much you're matching. So the objective function is a bit different. It's not clear.
Obviously, he's constrained as to not be able to apply the matchings as frequently as the arrivals.
He's constrained, or
He must be, right? If the queues are getting big, he must be constrained if he can't match things up as frequently as things.
oh yes, yes.
Right. In your model, you can do a matching whenever you want. Right. You have no timing constraint on when you do matchings, as long as you have
No.
supply there.
But my constraint is that in order to do a matching, I have to have enough supply of the other.
That's correct.
And he removed that constraint because he says that all queues always have enough demand.
So he has to
So
have
that's
a
a constraint that
he can't do matchings very frequently. Otherwise, that wouldn't happen.
Instantaneous service.
no. So I think he still has. So that's a good point. I think he still has instantaneous service. I think he kind of
He doesn't have an arrival process.
he doesn't have enough. He has, I think, in arrivals he doesn't have enough arrivals of some, which will guarantee that others. So you're right. Not all queues can be very positive in a setting. Only some of them.
I see.
Yeah, but you're right. Otherwise, you have to either limit the speed, or you have some under input streams that are too slow. Right. Yeah. So yeah, I guess that's true. I don't remember exactly the setting of his paper, but his objective function was somewhat different, and the queues he cared about, in some sense, were always very, very big. So he makes some assumption about being able to match everyone. Yeah.
On the discrete review time.
Yes.
It seems like the cost function doesn't come in there in that, at least directly.
Yes.
If your cost is increasing very rapidly, you would want to do the review much more frequently if the cost is up.
Yeah. So what happens is, if the cost is Lipschitz, you get the square root of n. If the cost goes up faster, you actually get a worse error bound. So you're right in that sense, but still the relation between our error but then also the absolute cost goes up, significantly up. So you can still use the same. You cannot tweak enough the review time, the review epochs to compensate for that fast increase. So we absorb. So the general statement has weaker results in this, if it's not Lipschitz.
Another question? Thank you very much.
Thank you.